In section 19, we're exploring triangle similarity, what it means to be similar, and maybe some shortcuts that we can have to demonstrate similarity a little bit quicker. So in our warm-up here, for each pair of shapes, we're going to find the ratio of the small figure to the large figure. So we're looking at corresponding parts, and these are parts of the two shapes that line up. So in other words, if we were to kind of change the size of it, they would overlap each other. So if we look at 9 and 27, those are overlapping pieces. So 9 over 27 is our ratio of the smaller figure to the larger figure. So we're going to call that a 1:3 ratio because we'll want to reduce it. Same thing with 12 to 21. So we're going to put 12 divided by 21. We're going to take a 3 out of each of those to reduce it. And we're going to get 4 out of 7. In activity 1A, we were given triangle cutouts. So we had these triangles that we had cut out and then matched them up. We asked to sort them based on a characteristic, trying to see which ones were similar. So the correct sorting was triangle A, H, and G. And what ends up happening is those triangles were the same shape, but different sizes. So we call those similar. Same thing with triangle C, triangle I, triangle F, and triangle B, D, and E. Those triangles, again, were the same shape, but a different size. So they're similar. So why did we choose that? Because the triangles in each set have the same shape but are different size. That's what we're calling similar triangles. So then we explored some measurements of those. We took triangle A, H, and G, and we measured the angles using a protractor. We said that angle 1 was the right angle, or what appeared to be the right angle. It turned out it was. And for each of those triangles, notice that each of the 3 angles were 90 degrees. It's exactly kind of what we expected to happen. Angle 2, one of the other angles that corresponded, again, we want to make sure that they lined up in the correct spot. Those are all 37. And then our third angle was 53. So our conclusion from this is that the 3 angles are the same, or 3 pairs of corresponding angles are the same. So when we have 3 pairs of angles, 3 pairs of corresponding angles, that are the same, we can conclude that the triangles are similar, so it appears. Let's take a look at the sides then. So in this set, we looked at triangle C, triangle I, and triangle F, and we matched up the corresponding sides. We looked at the large triangle and the medium triangle of that set. We measured the length of side 1, the corresponding sides. We got 8.8 and also 13.3 in the medium. Did the same thing for side 2. We got 5.1 and 7.6, and side 3, 5 and 7.5. Our measurements might vary a little bit depending on who's actually taking the measurements. You might read it wrong a little bit, or the error in the measuring tool. But we want to find the ratio of the sides of B to A, so the medium triangle to the small triangle. Ends up turning out that we're very, very close to being the same throughout. We have 1.51, 1.49, 1.50. So it looks like our corresponding, or the ratio of the corresponding sides is 1.5. Did the same thing for the medium triangle and the large triangle, 13.3 and 17.5, 7.6 and 10.1, 7.5 and 10. Found the ratio of the large triangle to the medium triangle. It's 1.32, 1.33, 1.33. So we're going to call that 1.33. And then the same for the small triangle and the large triangle. 8.8 and 17.5, 5.1 and 10.1, 5 and 10, and we're about 2 for the ratio. Now, what's cool about that is this kind of connects back to what we did before with dilations, and that we're taking one triangle and we're resizing it. So when we resize it, this number right here is the scale factor of the triangles. So the small triangle compared to the medium triangle, the medium triangle is 1.5 times the size for all the sides. And the medium triangle to the large triangle is 1.33 times the size from the medium to the large. And for the small, you take the small sides, you double them, and you get the large triangle. So our conclusions here are that in set 1, we call this triangle similar because they were the same shape, different size. We can conclude that the angles of the similar triangles, the corresponding angles, are congruent. Every single corresponding angle matched up with another one in the other triangle. And for the sides, we looked at that with set 2, the corresponding sides are what are called proportional. That if I found the ratio of any of the sides, as long as they're corresponding, they should be equal when we're looking at the same triangles. So if I'm looking at the small triangle and the large triangle, each of those ratios, and I know they're not exact, but they're really darn close, are going to be the same, 2. Same thing with the medium to the large. These sides were 1.3 times as big as those sides on average. So that's what our definition of similar triangles are. They're triangles that the corresponding angles are congruent and the corresponding sides are proportional. But if we're trying to show that these things are always true, we don't necessarily need all that information. But let's say make sure that we know how to actually resize these triangles. So let's say we have a triangle. We had set 3, and we took the length of side 1 and side 2 and side 3 in the large triangle. We also measured the angles, 74, 53, and 55. So what ends up happening is we're trying to resize this. The small and the large triangle are similar and have a scale factor of 1/4, which means the small triangle is 1/4 the size of the large triangle. So we take that triangle, 15.4, we divide it by 4, and we end up getting 3.9. And that's that small measurement right there. We take 13, we divide it by 4, we get 3.3. The medium and large triangle have a scale factor of 1/2, so take each of those 3 measurements and divide by 2. Now for the angles, we don't resize them. Again, the corresponding angles of similar triangles are the same. They don't change sizes. If they did, our fact of the angles of a triangle adding up to 180 degrees would no longer hold true. And that would be a major concern for us. So our angles don't change their size, but the sides definitely do, and it's based on that scale factor. In Activity 2, we looked at some shortcuts, some ways that we can kind of maybe get it done a little bit quicker than having to show that everything is the same. Either the angles are congruent or the sides have the same ratio. So again, just reviewing, corresponding sides are proportional, corresponding angles are congruent. The nice thing is we have 3 different shortcuts that we can use. One is called angle-angle similarity. What it basically says is if we can show that 2 pairs of corresponding angles are congruent between the 2 triangles, then that shows us that the triangles are similar. Similarly, we can show that we have a side-angle-side relationship. 2 pairs of sides, corresponding sides, are proportional, meaning the ratio is the same, and we have what's called an included angle. And an included angle is the one between the congruent sides. So the sides have to have the same proportion. The angles have to be congruent. If that's the case, then the triangles are similar. Or we can show side-side-side similarity. And what that does is show that all 3 pairs of sides are proportional. The ratio of all 3 pairs of corresponding sides are equal. And those would show similar triangles. Again, we saw that back here when we had the ratio of the 3 pairs of sides were exactly the same. Or pretty darn close. Again, we measured it, so it wasn't exactly perfect. So in this last part of the activity, we want to know for each of the following, identify which triangles you could demonstrate are similar, and then the shortcut you would use. So number 3, when we have these lines right here with the arrows, that indicates that those lines are parallel. So what I want to do then is I want to show that these angles are the same. And I know they're the same because they're corresponding angles. Corresponding angles when lines are parallel are congruent. Same thing here. Those are going to be the same. So what we're going to do then is show that we have 2 pairs of congruent angles, which we've got right there. We look at this triangle as being one piece of the puzzle, and then we look at this triangle as the other piece of the puzzle. And what we're showing here is that we have 2 triangles. What I'm looking for then is the corresponding pieces. So I know that this angle right here, angle B, matches up in both triangles. It's in the same position. It's the same angle because it's overlapping. It's the same thing. Then we look at these 2 angles here. Let's do it in yellow. So if we're just simplifying, we're just going to use one letter. I know that's technically not correct because there's 3 letters we should use to name that one. But for correspondence, it works. We're looking for angle A, and the other angle that matches up with A is this one up here, the D. And the third angle, again, it should match up because, well, it has to. E and C match up. So that's how we're going to name that triangle, BDE or BAC. The order doesn't matter as long as you're consistent. What I mean by that is you could start with D, but if you start with D in this triangle, you have to start with A in the other triangle because that's the corresponding angle. If you started with E, you'd have to start with C. Now again, our shortcut there would be angle-angle similarity because I've got two pairs of angles the same. Looking at number 4, we have 3 compared to 6, 4 compared to 8. 3 to 6 is 1/2, 4 to 8 is also 1/2. So I've got two pairs of sides that have the same ratio, they're proportional. And then I also have this angle right here, the one between the sides that we've been talking about, are congruent. So if that's the case, I have a side-angle-side relationship. So now it's just a matter of, okay, how are we going to name it? So if we start with S, S and N are in the same spot when we name it. R, wrong highlighter, hold on. Let's fix that. R and E match up. And T and I match up. And again, that's a side-angle-side relationship because 3 over 6, and let's go ahead and write that. 3 over 6 is 1/2, as is 4 over 8. We've got the same ratio of sides. The triangles have to be similar because of that SAS relationship. And let's see, let's look at number 7, last type here. So again, I'm looking for corresponding pieces. I've only seen sides mentioned, so I'm pretty confident in side, side, side. But let's just verify that it actually is and make sure we name it correctly. So looking at the two triangles, I'm going to look at the big piece. The big piece right here is the 20. And in this triangle, it's 24. So I'm going to compare those. 20 to 24. That's 5 to 6. I'm going to do the same thing with my next side here, 15 and 18. So I'm going to compare 15 to 18. 5 to 6. And I'm going to do the same with 10. Oh. There we go. 10 and 12. 5 to 6. The ratios are all the same. So then we're looking at the pieces and where they match up. So if I start with K, based on how this goes, if I go from K to L, I've got to go through that green segment. So that looks like I'm going to start with R because K is between the green and the red, and R is between the green and the red. And that goes to Q and the P. So K, L, M, R, Q, P. Got to make sure the pieces are in the right spot. So those triangles are similar by our third and final one, the side-side-side similarity. So here we looked at what are the corresponding pieces of the similar triangles going to look like, and how do we show that they're the same?